The drawback of the conventional AM system, we have learned in our previous lecture that the major drawback of amplitude modulation is that in the modulated signal, the carrier signal is also transmitted. See, ultimately, we want only the message signal to be recovered at the receiver end. In the AM signal, if you see, we have a carrier signal as a separate element, and we have the upper and the lower sidebands. So this carrier signal is unnecessarily, it is occupying the bandwidth. So the carrier signal does not contain any information. Therefore, a lot of transmitted power is wasted in the transmission of the carrier signal. Even in the most efficient case, when modulation index is 1, 66.67% of the transmitted power is wasted in the transmission of the carrier. So if you see how much is the carrier power alone, okay, it will occupy around 66.67% of the total transmitted power. So it is unnecessary. So we can eliminate the carrier. Okay, so that's what we are going to suppress the carrier. For lower values of modulation index, the power wasted is even more. So when we have the higher modulation index, when modulation index is maximum, it is 1. So this much, 66.67% of the total power is wasted. So when the modulation index is still less, the power wastage will be still high. So that's why we go for the other variants in order to improve the overall system efficiency. So why DSBSC? So that is, we are going to use the double sideband with suppressed carrier. So we are going to remove the carrier, suppress it, and then generate a AM signal. So the total carrier power will be 2/3 of the total AM power. That is the total transmitted power, 2/3 of the total transmitted power. Thus 2/3 of the total AM power is utilized for the transmission of the carrier component, which does not bear any message. A significant saving in power requirement can be achieved by suppressing the carrier before the transmission. So this led to the first variant of the AM, which is termed as DSBSC. So this is the first variant, which is called double sideband suppressed carrier. So still AM is in use. So we have the other variants. Then why are we using the conventional AM? The significant power saving in case of DSBSC does not come without a price. So when we go for the other variants, the system complexity will definitely increase. So DSBSC adds complexity at the receiving point to recover the message. So depending on the application, the conventional AM or DSBSC can be used. So either we can use any system depending on the need and the application. Okay. So what is called DSBSC? So it is double sideband suppressed carrier. So the carrier signal is suppressed. Modulated wave will contain only the upper and the lower sidebands. Transmitted power will be saved since we are suppressing the carrier. So bandwidth will be the same of the conventional AM, that is the double sideband full carrier AM. So we have the two sidebands along with the carrier signal. The bandwidth is twice of the modulating frequency. Here also, in DSBSC also, the bandwidth will remain the same, which is twice of FM. So this is the time domain representation of a DSBSC-AM wave. So here for generating a AM DSBSC waveform, we are going to use a product modulator. So here we have the two inputs. One is the message signal, which is X of t, and this is the carrier signal, cos omega ct. And this product modulator will simply multiply this, and we have the modulated signal or DSBSC signal, which is then transmitted via an antenna. So this is the modulating signal. So let the modulating signal mathematically be expressed as Vm of t, which is Em into cos omega m t plus phi m. So here we are expressing the message signal or the modulating signal in the instantaneously. So we are representing in terms of time with respect to time. So we have the maximum amplitude, which is Em max, and the minimum amplitude, that is positive and the negative peaks. So this is simply a cosine wave. Okay, so this is Vm of t. So this is varying with time. So this frequency Fm equal to 1 by Tm. We are expressing the carrier signal. So carrier signal is mathematically expressed as Vc of t. So this is again instantaneous. So we are taking the carrier signal with respect to time. So it is Ec cos omega ct plus phi c. So this omega c is the frequency of the carrier, angular frequency, and phi c is the phase. And here again we are taking a cosine wave. So Ec max is the maximum amplitude, and minus Ec max is the minimum amplitude, positive and the negative peaks. Tc is the time period. So Fc is 1 by Tc. So always Fc should be greater than Fm. So next, So now we are going to generate the DSBSC by simply taking the product of both, that is the message and the carrier waveforms. So this DSBSC in terms of time is represented as Vm of t into Vc of t. So we are just taking the product of both, and so finally we are arriving at this a DSBSC waveform. So if you take the product of both, it is Em into Ec by 2 cos omega c minus omega m plus cos omega c plus omega m. So we are just using the same trigonometric identity. We are getting only the two side bands, upper and the lower side bands. So if you compare this fifth equation with the conventional AM, so this is a conventional AM waveform, we have the carrier component, and here we have only the upper and the lower side bands. So this is the frequency spectrum. So frequency spectrum, we have suppressed the carrier, and only the side bands are allowed for the transmission. We have the upper and the lower side bands. So the bandwidth we are going to calculate using the upper and the lower side band. So which is maximum positive frequency minus the lowest positive frequency. So we have the bandwidth Fc plus Fm minus of Fc minus Fm. So it is again twice of Fm. So bandwidth of DSBSC is same as that of the AM signal. Okay, and if you see the waveform, so this you can find the difference in the time domain representation. So this is the modulating signal, and this is our conventional AM system, AM waveform, and this will be the double sideband with suppressed carrier. So this is the difference. Some difference you are identifying in the Vmin values. Okay, so this will be the double sideband suppressed carrier wave. And this is the phasor diagram. So phasor diagram, the carrier is suppressed, indicated by dotted line. So we have this upper and the lower sideband representation, and this is the carrier signal which has been suppressed, and so it is indicated by dotted lines. So now we are going to calculate the efficiency of the DSBSC waveform. So for this we need the total power. So the total power in our AM double sideband full carrier is expressed as carrier power plus upper sideband plus lower sideband. So we know this this expression we have already studied. The total power will be the carrier power into 1 plus m square by 2. So now when we are calculating the total power in case of a double sideband suppressed carrier, the carrier component is removed, right? So let us express it as PT dash, which is the sum of the upper and the lower sideband power. So this will be m square by 2 into PC. So if you just add only the upper and the lower sideband power, it is m square by 2 into PC. So now let us calculate the power, how much power we are going to save. So here we are finding the difference between the total power, that is the power in the AM wave minus the power in the DSBSC wave divided by the total power. So then we can find what is the power which that we are going to save. So now using the third and the fifth equations, we are just substituting here. And so if you substitute and simplify, so this expression is 2 by 2 plus m square. Okay, so from this expression, if you take the maximum modulation index as 1, if m is 1, this will be around 2 by 3, so which is around 66.7%. So this will be the amount of power that we are going to save when we are going to suppress the carrier. So how do you calculate the modulation efficiency? So it specifies the share of sideband power in the total power of the AM signal. So now when you want to calculate it for the DSBSC, so this is the sideband power divided by the total power. Efficiency eta is defined as sideband power by the total power. So since the carrier is not transmitted in the message signal, so for DSBSC, total power also will be equal to the sideband power, because we are transmitting only the sideband and we are suppressing the carrier. So the modulation efficiency here will be 100%. For DSBSC waveform, the modulation efficiency will be 100%. Let us see about the generation. So different modulators, what are we using for generation of DSBSC AM wave? So we have two types of AM DSBSC generation. One is called the balanced modulator, and the other one is called the ring modulator. Okay, let us study about what is called a balanced modulator. So this is the circuit for balanced modulator. So here we are using two transistors, T1 and T2, and we have a modulating signal Vm cos omega mt. So this is applied as in a push-pull fashion. So we have a VM. So we have a transformer here, and VM. We have the positive VM and minus VM. So we have the other VM which is shifted in phase. So this modulating signal is applied in a push-pull fashion, and the carrier signal is applied in parallel at both the transistors T1 and T2. Okay, and at the output we are going to add this current I1 and I1 dash. So whatever output that we are getting at both these transistors are simply going to be added at the output. So finally we will generate a DSBSC waveform. Let us see how we are generating based on equations. So here two nonlinear devices are connected in balanced mode. Two transistors are identical and the circuit is symmetrical. So here is the circuit is almost symmetrical, except that at the output of the center tap transformer we are having VM, and that is the modulating signal is given in phase and out of phase at the input of the two transistors. So voltage across the windings of the center tap transformer is equal and they are opposite in phase. So we have VM dash, which is minus VM. So with here VM and this is minus VM, which is applied as input to the transistor T1 and T2 respectively. And this VBC and VB-C are the two inputs, which is going to take both modulating and the carrier signals at the input of the base of T1 and T2. So you can see we will mathematically derive what will be the input VBC and VB-C. So modulating signal is fed in push-pull and the carrier voltage is fed in parallel to a pair of identical transistors. The carrier voltage is thus applied to the two transistors in phase and the modulating signal appears 180° out of phase. So here this modulating signal is out of phase, carrier signal is in phase. So now let us see the mathematically how we are going to calculate VBC. So this VBC will be the input which is applied at the base of transistor T1. So let us calculate VBC. The input voltage to the transistor T1, it is expressed as VBC. So which is sum of the carrier signal plus the modulating signal. So we are adding the carrier signal and the modulating signal. So this is the input to the transistor T1, which is VBC. So let us take it as equation 2. Okay. And input to the transistor T2 will be VB-C. So this is simply the notation we are taking. Simply VB-C will be the sum of VM dash and the carrier signal. So let us add VC of T plus VM dash of T. So this VM dash is nothing but minus VM. So this is VB dash T. Let us take it as equation 4, which are the inputs to the two transistors. So now these two transistors are working in the nonlinear operation. Okay. So you using the nonlinearity property, the output or the collector current can be expressed as, so this is output I1. So this is the I1 is the output of the first transistor T1. So which is expressed as A into the input voltage plus B into input voltage square. Similarly, for the second transistor T2, I1 dash, let it be the output collector current, which is A into the input voltage plus B into the square of the input voltage. So now in this equation 5 and 6, we are going to substitute 2 and 4. Okay. So after we substitute the second equation in 5, and again we are going to take we are going to expand this a plus b whole square form. So in this we are just expanding a plus b whole square, which is bc square cos square omega ct plus vm square cos square omega mt plus 2 into cos a into cos b. So this is equation number 8. And similarly we are substituting the fourth equation, this fourth equation in sixth equation, and again we expand this. So this will be a minus b whole square form. So this we are just expanding. So this is, let us take it as equation 8 and 10. Finally, at the output of the transistor T1 and T2, we are going to combine both the signals. Okay. So after we combine, this is the output voltage. The output AM voltage is given by V0, which is K into I1 minus I1 dash. So we are taking the difference of the two outputs. So if you take this difference, just take the difference. So common terms will cancel. So this VC cos omega ct minus VC cos omega ct will be cancelled. And we will have twice of VM cos omega mt. And similarly, from 8th and 10th equations, VC square cos omega ct plus VM square cos omega mt, both will cancel. Finally, we have 4 times of VC VM cos omega C T and cos omega MT. So that's what we will obtain here at this output. We will have K into 2A VM cos omega MT plus K into 4B VC VM cos omega CT cos omega MT. So this will be the final output where we have suppressed the carrier. The carrier component, which is as a single component, we have suppressed. So from this again, we are just taking the constant term outside. So we can take this entire first term, which is common, cos omega MT into 2K, VM is constant. And this, if you take this A also outside, so we can divide the second term by A. So we are taking this entire term outside. So it becomes 1 plus 2B VC cos omega CT by A. So this 2B into VC by A, we are taking it as a modulation index, which is M.